Hello everyone, welcome back. In this video, we'll be discussing about the second and the fourth problem of yesterday's biweekly contest. Find the number of ways to place people 2 and find the number of ways to place people 1. Both the problems are exactly similar. The only difference lies in the constraint. Here n is less than or equals to 50 and in this problem n is less than or equals to 1000. As always, we'll start from the very brute force solution and optimize it step by step. So let's get started. The problem states that you're given 2D array points of size n cross 2 representing integer coordinates of some points on the 2D plane. So points I will represent xi comma yi, right? Now you have to place n people including Chisato and Takina at these points such that there is exactly one person at every point. So basically each point represents one person, and among those persons there are two specific persons we care about, Chisato and Takina. They are also in one of these 2 points. Now the condition is Chisato should be at the upper left corner and Takina should be at the lower right corner of the rectangle which will be formed by taking Chitaso's point and Takina's point. So that rectangle will be a fence and Chisato don't want anyone else to be in the fence, right? So otherwise Chisato would be sad. You have to return the number of pair of points where you can place these two guys, Chisato and Takina, such that Chisato doesn't become sad on building the fence. So let's take an example. Let's say there are these 2 points. If there are these 2 points, you can't build a fence at all such that Chisato will be happy. So Chisato will only be happy when Chisato is at the top left corner of the rectangle and Takina is at the bottom right corner of the rectangle. So in this case, if Chisato is here and Takina is here, the first condition itself is not satisfied. Chisato is not at the top left corner. If you place Chisato, let's say at top left corner, and Takina is also not at bottom right, Takina is at 1 1, then also this is not a scenario where Chisato will be happy. So Chisato will only be happy when Chisato is at the top left, Takina is at the bottom right, and there is no other person in the fence. That is, there is no other point in this entire rectangle other than these 2 points. So let's take some examples. Let's say these are the 3 points that are given, or other words, there are 3 positions where you can stand a person, and among these 2 points, one of the way where Chisato will be happy is you place Chisato as 4 4, Takina at 6 2. In this case, Chisato is at the top left corner, Takina is at the bottom right corner, and if you build a fence around this in the rectangular fashion, there is no other people in this fence, and hence Chisato will be happy. So this is one valid way where Chisato will be happy. Another valid way would be Chisato is at 2 6 and Takina is at 4 4. So in this case as well, you can see there you can build a fence such that there is no one else inside the fence, and Chisato is at the top left and Takina is at the bottom right. Now finally, this is another way to build a rectangle, but in this case Chisato will not be happy. Even though Chisato is at the top left and Takina is at the bottom right, inside the rectangle or inside the fence there will be another person as well, so Chisato will not be happy. So in total there are only 2 ways to place Chisato and Takina at such positions such that Chisato will be happy, and hence the answer here is 2. So hope the problem statement is clear. Now how to solve this? So let's just think about the brute force solution. If you haven't thought about the brute force solution yet, I would encourage you to pause and try to think about the brute force solution first at least. So notice we need to form rectangles, and we need to put Chisato at the top left and Takina at the bottom right. So let's say you take all possible top left values. So you said, okay, L denotes the position of Chisato, which will be the top left, or which should be the top left of the rectangle, and let's assume that R denotes the position of Takina, which ideally should be the bottom right for Chisato to be happy. Now once you are iterating, you have fixed L and R, that is, you are trying out all possible values of L and R. Now in this case, what are the conditions for which this L and R to be valid? So this L and R is valid if L is at the top right and R is at the bottom. L is at the top left and R is at the bottom right. In other words, the x coordinate of L should be less than equals to R coordinate of x coordinate of R. Similarly, y coordinate of L should be greater than equals to y coordinate of R. So if that's satisfied, then the first condition, that is Chisato should be at the top left and Takina should be at the bottom right, is satisfied, right? So this you can check in just order one time. Now what you also need to check whether there is anyone inside this rectangle or not. So how will you do that? One of the ways could be just iterate over all other points and see how many points are inside this rectangle. How you can figure out that? You simply iterate over the points and see their x and y coordinates, whether their y coordinate lie between this and this, or their x coordinates lie between this and this, right? So if that's the case, that is a point that is inside this fence, and hence this particular value of L and R will not be valid, or in other words, Chisato will not be happy if you place Chisato at here and Takina at here, right? So this is one valid solution. Now what will be the time complexity of this entire solution? You are trying out all possible values of L and R. So you are placing Chisato at every possible positions and you are placing Takina at every possible position. So in total you are trying out n square pairs of point, right? Or n square different possibilities of placing Chisato and Takina. Now you need to understand whether each of these are a valid position or not. So for that, what you are doing, you have to first check whether it is at the top left, Chisato is at the top left and Takina is at the bottom right. For that you just need to do some mathematical computations that will take you order one time, right? After you ensure that Chisato and Takina is at the top left and the bottom right respectively, you can simply iterate over all other points and see how many lies within this fence. For that you just need order and time, because you are iterating over each of the points and doing some mathematical calculations to understand whether it is inside the fence or outside the fence. So in total, the complexity of this entire brute force algorithm is order n cube, right? So this n cube algorithm will work for the second problem, that is people 1 here, where n is 50. So you can use, like, if you haven't come up with this n cube algorithm by yourself, I think it's the right time you will pause the video and try to code this n cube algorithm by yourself to get a better understanding. Now this solution will not work for the last problem, that is ways to place people 2, because here the value of n is 1000. So n cube will not fit in the given time constraint. So we have to optimize this. Now how will you optimize this? So notice there are 3 things here, or 3n here. 2 n's are coming from the fact that you are trying out all possible values of Chisato and Takina, and second n is coming from the fact that you, for each of those n's, you are iterating over all the other points and seeing whether they are inside the fence or outside the fence, right? So that's where this second n is coming from. Now removing an n from here would mean that you are not fixing Chisato's and Takina's position, and even before fixing that you are somehow able to figure out number of pairs, which is hard. So let's first try to focus on removing this particular n, that is, we want to find out how many points are there, or whether any points are there or not inside this fence in less than order n time, right? How will you do that? So notice that what you want no one to be there inside this particular area, right? So let's say you are trying out this particular R, right? and now in the next iteration you will try out some other r, let's say this r, right? So in that case this will be the rectangle you are trying out, right? So if you iterate over these rectangles and at that moment understand whether there is any point which you have visited previously, are they inside the rectangle or outside the rectangle? Because any points which is after this x will never contribute to this rectangle or will never end up lying in this rectangle at all, right? So what you can do, you can iterate over r in a sorted fashion, that is in the order of x, and whenever you visit any r, you note down its value of y. Okay, so in this case we know that we are visiting x in this order. Now we visited these 2 points, let's say first. So we know that we have a y at index 0, we have a y at index 2 or index 1, right? Now when you are visiting next star, let's say you are visiting next star, which is this. So first of all you can simply check the first condition, which will take you order 1 time. So if it is not satisfying the first condition itself, you don't need to move forward, you can simply go ahead for this next one. So if it satisfies, so in this criteria this L and this R satisfies the first criteria, because this, the value, this will be the top left and this will be the bottom right if you form a rectangle here. So in this case, for no one to be here in this rectangle, what should be your criteria? The criteria should be whichever points you have visited so far, or whichever points is before R, all those points shouldn't be in this range. In other words, for all those points the value of y should not be in this range, right? So what you can do, you can simply figure out the lower bound of R and also the lower or upper bound of L, and see if there are any elements in between them or not. If there are, you know there will be 1 point within it. If there are no, then you know you can be assured that if you place Chisato at this L and Takina at this R, there will be no one inside this particular fence, right? So just to reiterate this part, what we are doing, we saw that if we iterate over R in a straight line fashion or in an increasing order of x, first of all we don't need to care about any of the x which we haven't been visited so far. Now because we only care about the x which we have visited so far, we can do some kind of pre-computations for all those x, right? So we have visited these 4 points so far, let's say. So for all these points I can simply maintain, or rather this is the current R, so we have visited all these points. So for all these points I can simply maintain what is the value of y I have seen. So I have seen a value of y at 0, I have seen a value of y at 1, and I have seen a value of y at 5, right? Now when I am visiting a particular R, I can simply see what is the value of this particular y. This is 2. So where does 2 lies? Does it lie or in between 2 and 5 or 2 and 4? Is there anything in between that? If the answer is no, we are good. So basically if you do upper bound of 2, you will get 5, right? If you do upper bound of 4, you will again get 5. It means there is nothing in between 2 and 4, and because there is nothing in between 2 and 4, you are sorted here, right? Basically there is no one inside this fence, you can assure that. Now once you have visited this R, you will also add this to your list or to your data structure and move forward. So let's say let's just take one last example. Let's say you have added this R as well. Now you are visiting this point. So if we are visiting this point, first condition satisfied because this will be the top left and this will be the bottom right if you form a rectangle here, right? Now second condition is in between 4 and 1 there should not be anything, right? So let's figure out the upper bound of 1, which is 4, right? Let's just figure out the upper bound of 4, which is again 4. So basically there is a element which actually lies in between or in the border of 1 and 4, and because there is an element, it means there is a point which is there, right? So okay, sorry, I think we have to insert 2 here, not 4, right? Sorry. And if you just do upper bound and lower bound, you will see 2 will be there in this range. So hence in between this L and this R, if you form a rectangle, there will be 1 point for sure which has the y value of 2, and hence this R will not be a valid one. You will try out any other R, right? So hope you get the idea. So what we are doing, we simply iterate over R in a specific order, that is in increasing order of x, and whenever we reach a y, we simply check if there is anything in between the y value of Chisato's position and current R. If there is anything, this R is not a valid R, I will try out other R. If there is nothing, this R is a valid R, right? So what will be the time complexity now? So notice what you are doing, you are maintaining a data structure that will keep the indexes sorted and can also help you find out upper bound or lower bound efficiently. So this data structure you can use set or any self-balanced Panini tree that will give you upper bound and lower bound in just log n time, and it can also do insertion in just log n time. So overall you will be doing n insertions for a single n. So there are total n possible values of L. For each of these L, you will be trying out every R. So there are n R, and for each R, what you are doing, you are first checking whether so first of all there is n possible R. Now for each R, what you are doing, you are first checking whether this L and this R are in the top left and top right. So for that you will take order 1 time, right? So let's ignore that. Secondly, you are checking how many numbers are in between this y of L and y of R. So for that you are doing upper bound or lower bound on the value of y value of L and y value of R. So that will take you 2 log n time, and after doing that you are also inserting this R into the y value of this R into your data structure. So that will again take you log n time, right? So overall the complexity is now n squared log n, which is lot better than the n cube complexity, and this may or may not pass for this problem depending on how you code it. So because of a small constant factor as well, this may or may not pass. So we can optimize it even further. Now again, if we want to optimize it even further, which of these factors will you be optimizing? Obviously optimizing anything from this n square requires more thought process, so let's just try to revert this log n from this complexity if possible first. So where from this log n coming from? Because we are maintaining a set of all the visited values of y, and also checking, and why we have maintained that, because we have to check if there is anything in between the y value of L and R. If there is, I will say no. If there is not, I will say yes for the current value of R. So notice you don't need to find out what exactly lies after in between L and R. You just need yes or no answer, right? So for that you can do something smarter. Notice, for let's forget about every other y or every other R. You are only considering all the points at a single x, right? So you are only considering all the points that are at x equals to 2. Now from all these points, which of the points can contribute to this, or can be a valid position of Takina for this particular position of Chisato? The answer is only the one which has the maximum value of y. Other points will not be a valid candidate, because if this point is not a valid candidate, then this point for sure is not a valid candidate, because in this rectangle, in the rectangle below one, in this particular rectangle, we are sure that at least this point will be lying on the fence, right? Because this point will be lying on the fence, there is no point at all to consider this value or this point for a valid value of r. This will always be invalid r if there is an r above it, right? So for any given value of x, we only want to check the y which is the maximum. Now notice that not only the maximum, we want to check the one which has the maximum value that is less than equals to the value of y of L. So in this particular case, there are 3 points. We don't want to check r for this one, because that we are sure that it will never be possible with this r, because if you pick this as r, Chisato will not be at the top left of the rectangle, because the rectangle formed will be something like this. So Chisato will not be at the top left. So we have to find, or we have to only consider the r which is less than equals to the y value of this L, and all other points we can ignore. So in this particular case, this is the first point for which the y value is less than equals to L. So we can simply ignore other points, because none of the other points will be a valid value of r for this particular x, right? So that, hope that makes sense. So we are saying that for a single x, we have reduced our candidates to just one, right? Either that will be the answer, or there is no valid candidate for this particular x, right? Now let's say this is your first x after this x. So this is the value of x for just Chisato. So this will be the first x for Takina, let's say. Now in this case, for first x, it will surely be a valid candidate, because in this case we haven't visited, or we haven't encountered any other position. Notice that if there is a point here, this will be your first x, and for this it will be valid, but this may or may not be valid. So the first point that we encounter will always be valid. So this is a valid position for Chisato and Takina, and Chisato will be happy. Now for the next x, in this particular case, this doesn't have any valid x. In this case, this is a valid x. Now for this x, we want to check if there is anything in between this L, the value of y at this L and this r. So we want to check whether there is anything in between this, right? So if you have already visited a point whose y is greater than the y of current r, then no matter what you do, this point will always be inside this fence. If that's not the case, then this point will always be outside the fence. So in this particular case, the value of y for the point that we have visited previously, or that's a valid y for Takina previously, if the value of that point is greater than, or the y value of that point is greater than the y value of the current one in consideration, then we are sure that this point will be inside the fence, otherwise this point will be outside. So in this particular case, the y value of this point is greater than the y value of the previous one, so this will be a valid position, right? So again, one last time, so let's say this was the last fence that you have built. Now whatever fence you will build, that fence should not cross this point at all. So whatever fence you will build now will look something like this. right? So we'll never cross this point at all. So if that fence crosses this point, then the next fence that you are building is not a valid fence, right? So for this condition to be satisfied, whatever point you have, the value of that, the y value of that should be greater than the y value of this particular point, right? So what we are saying is we only care about whether the y value is greater than the y value of the previous good point. If it is greater than the y value of previous good point, we are sure that there is no other point at all in this fence. If that's not the case, then we are certain that there will be a point inside the fence which we are building right now. So let's say for this particular r, if we are building this particular fence, because the y value is not greater, it means this point is also there inside the fence, right? So hope this entire thing makes sense. So from this, we now no need to maintain this set at all. We just need what is the max value of y which we have seen so far, and based on that we'll decide whether the current one is a valid one or not, right? So let's just do one small dry run before we conclude. So again, we are trying out all possible values of L and R, and we are trying out R in the sorted value of X. So we have sorted these indexes such that the smallest, the one which have the smallest value of X will be first in the list, one which have the largest value of X will be last in the list. Now among the ones which have the same value of X, we only care about the ones with the highest y first. So if the value of X is equal, we'll sort the list based on the value of y. The highest y will come first, right? Now once we have done this, we'll try out every possible L and R. So let's say we are trying out this L. Now we'll try out every other R. So for this R, we'll simply check the first condition first of all. So the first condition is whether the X value of this is less than equals to this and Y value of this is less than equals to this. If that's there, we will simply check what is the maximum Y we have seen so far, or the maximum Y of a good index that we have seen so far. So there is no good index at all right now, so there is no maximum y at all. So maximum y is minus infinity, right? So because maximum y is minus infinity, we can take this point, or this is a valid point, so we'll simply take this, and our answer will be incremented by 1 for this particular L. So let's try out the next R. So again, before trying out next R, we will simply update the maximum value of y we have seen so far, that is 1, right? Because this is a valid point, and for this the y value is 1. Now for this R, you will simply check what is the maximum value of y you have seen so far. You have seen 1. The value of X y for this R is 0, so you will simply skip, right? Now this can be skipped with two ways. Either you will apply this algorithm, or you can simply apply a algorithm where you say for a single X I will just try out one possible Y, right? So that's how you will ignore this point. Now for this one, the first condition is not satisfied because Y is greater than the Y of this, so let's just move forward. For this one, the first condition is satisfied, so we'll see what is the maximum value of Y we have seen so far, 1. What is the current value of Y, 2. Is 2 greater than 1? Yes. So there is this fence will be a valid fence, there is no other point inside this. So because this is a valid fence, we will simply update our maximum value to 2, right? Now we'll try out next possible value of R. This is again not a valid value because this lies after, or the value of y is greater than the value of y at L. So we'll try out this one. This is a valid R because the maximum value of y we have seen so far is 2, and the value of y here is 4. So this is a valid value of X. So again, this will become 3. 1 was incremented here, I forgot to do that. Now once you have computed for this R, before going further, you will simply update the maximum value of y you have seen so far for a good index. Now for this one, this will not be valid because the y value is less than this. So finally this one, this will again not be valid because y value here is 2, which is less than 4. So in total for this particular L there are 3 code Ys. Similarly you will try out for this L next, for this L, for this and so on and so forth, right? So overall complexity is order n square. So if you watched to this point, I would strongly encourage you to pause and try to code this entire thing by yourself. It's very straightforward, you can code it within 10 lines. So next we're looking at the code. The code is exactly what we had discussed. So we simply sort the points in certain orders. The order is, if x value is equal, the one which have the greater y value will come first. If x value is not equal, the one which have the smaller x value will come first, right? Now once we have this point sorted in that fashion, we'll simply iterate over all possible values of x and y, or L and R, right? So this is top left and this is lower right. Now we'll first check whether this actually is the top left and this actually is the lower right. How? The value of x is already sorted, right? So we don't need to check for x, we'll simply check for y, which is the index 1. We'll simply check if the y value of the lower right is less than equals to the y value of the upper left. If that's not the case, if it is greater, then you will simply continue, because this will not be a valid point. Otherwise, if that is satisfied, that is you are at a valid value of r, let's say, so next you have to check what is the maximum y you have seen so far for a good index, right? So in this case we have initialized the maximum y we have seen so far for a good index is minus infinity. So the minimum y could be minus 10 power 9. So I have initialized with this minus 10 power 9 minus 1. So minus infinity kind of. So if the one that we have seen so far is greater than the current value of y, it means, so in this case when you are at this particular index, the maximum value of y you have seen that at that time was 4. So if it is greater, you will simply skip this. This is not a valid value of r again. So if that's the point, you will simply skip. Otherwise you will increment, this is a valid value of r, you will increment the value answer and also increment your max y. So notice you don't need to do max y equals to max of max y comma this, because you are sure that you will be coming here only when the value of y is greater. So you will simply equate this with LR of 1, right? So after doing this, answer will contain all the valid pairs and you will return the answer. So hope this entire solution makes sense. If you need doubts, feel free to follow up in the comment.